Thank you, Stefan. And as Stefan said, I'm Adwait Nadkarni, and I'm going to talk about making data secrecy enforcement practical on Android. So these operating systems like Android and iOS are very different from your traditional Windows desktop. For instance, on Android, applications are security principles. And simply what that means is that applications execute with a small subset of the user's overall security privileges. And these privileges are tied to their identities as security principles. So this is very different from your Windows desktop, where an application executes as the user and has all the privileges that the user has on the system. Now, since applications are security principles on Android, applications cannot normally access each other's data. So when the user wants to combine different applications, applications must share data. And I'll give you an example of how this sharing takes place. So say you get an email in an email application, and the email consists of an attachment. Now you click on the attachment, and the attachment opens up in a document viewer. And this flow is very seamless. What's happening in the background is that the email application is sharing the attachment with the document viewer. Now this sharing is really useful. You could then convert the attachment to a different format, or you could sign it with your physical signature, and you could even export it back through the email application, all within staying in the same workflow. At the same time, this sharing can be risky. What if one of these applications, say the document viewer application, decides to become malicious or is compromised and exports your data to a remote server on the internet? So the question for us is, how do we enable this data sharing amongst applications while also preventing such unauthorized disclosure of data? Now, if you look at it, the problem stems from the loss of control over the flow of shared data. That is, the email application can control sharing of data, but once this data is shared with an adversary, it loses all control over what the adversary does with it. So since this is a problem of controlling the flow of one's information, the solution is information flow control, right? Think about a secrecy model like Bella Padula. Now, information flow control has been around for over 4 decades, but it has seen very limited use in commodity operating systems. And one of the reasons for this is that most information flow control models require a centrally administered policy. And what this essentially means is that a system administrator sets the policy for system subjects and objects. Now, while this is reasonable to assume for system data, what about application-specific data like email attachments and notes and messages? A system administrator cannot be expected to reason about third-party applications like email, Gmail, and WhatsApp, let alone the secrecy policy for the data. So for application-specific data, we have decentralized information flow control, or DIFC. DIFC allows applications to become the data owners for their own secret data. And essentially, these data owners can create the security classes to mark which of the data is secret and which is not. They can even define the policy, define the secrecy policy for the security classes. That is, they can define the arrangement between these security classes, which defines the flow that is possible between them. And more importantly, they can define what declassification means for their own security classes. Now, to simply say this, declassification is the removal of the security policy. It is the removal of the label. And data owners can control when the label over the secret data might be removed. Now, to go back to the email example, the email application can easily protect its data by specifying a simple security policy. And the policy is as follows. The email application's policy allows every single data owner in the system to access and share its data with one another to give the user utility, but at the same time only allows the email application itself to declassify this information. Now, we are not presenting the first DIFC system for Android, but we have been working on integrating DIFC into Android for a while. So in 2013, we gave the first DIFC system for Android, that was Aquifer, and Aquifer focused mostly on DIFC policy for Android. Now, right about the same time, another group from CMU gave their own DIFC system for Android and proposed a non-interference proof for the DIFC system. Now, most recently, Xu and Mitchell have provided Maxoid, which gives some interesting storage level enforcement primitives for DIFC on Android. Now, while we have learned a lot of valuable lessons from these existing systems, what we have learned the most is that it's very hard to make DIFC enforcement that is both secure as well as backwards compatible with unmodified legacy applications. Essentially, what we observed was that if you want to provide really strong secrecy guarantees, then you risk breaking applications. But if you want to continue, if you want to work with unmodified legacy applications, then you have to loosen your security guarantees somewhere. So prior approaches have exposed three main challenges in DIFC enforcement on Android, namely determination of the subject granularity and labeling precision, the label change and propagation logic, and network declassification in a network-driven environment. And I'm going to explain all of these challenges individually, and then we're going to look at how we resolve these challenges in our system. So for subject granularity, we have two options. You have the fine-grained programming language variable that has the obvious advantage of precision, right? Fine-grained taint tracking is extremely precise. But at the same time, fine-grained taint tracking is susceptible to implicit flows in code. That is, flows that occur not due to the explicit transfer of information, but due to control flow. Now for security, what you really want is the granularity of the operating system process. The process is completely mediated by the operating system, so all the flows in and out of a process go through the operating system. But at the same time, the process is a very coarse-grained abstraction. Especially on Android, many instances of the same application may actually exist simultaneously in the same process. And these instances may be taking part in completely unrelated user tasks and dealing with completely unrelated user data. So when we restrict these different user tasks with the same secrecy policy or with a superset of all the secrecy policies, we actually have a lot of false positives. So what we really want for DIFC enforcement in terms of the subject granularity is the security of process level taint tracking without the false positives. Now in terms of label propagation, again we have two options. There is a class of system that proposes explicitly defining labels and explicitly changing labels on subjects. So if there are two subjects P and Q, and if P and Q have different labels right now, such systems expect P or Q or both to change their labels in time for any communication to occur. If P and Q don't adjust the labels in time, then the call is simply denied. Now explicit flows are very hard to model in Android, because on Android most communication is user directed and most sharing between applications is user directed. So applications aren't really aware of when they're going to be part of such communication. What we really need for Android is floating labels or implicit label propagation. So in floating labels, communication between different subjects is always enabled. But what happens is when P calls Q, the restrictions on P are propagated to Q. So the restrictions propagate in the direction of the flow of information. Now, while this is exactly what we want on Android because we want seamless communication, and while this propagation of restriction looks secure, floating labels as they are far from being secure or practical. So I'm now going to discuss an attack on floating labels that has been discussed in literature for a while. So say you have two processes, P and Q, and P has read the secret data bits 0, 1. Now P has also acquired the label L1 that is associated with the secret data. Now the objective of this attack is for P to propagate the data to Q without actually propagating the label. So obviously P is not going to directly call Q because that would propagate the label L1 to Q. Instead, Q creates two workers, Q1 and Q2, and these are also processes or subjects in the system. Now these workers, note that there are two workers for 2 bits, there's one worker per bit. Now all of these participants in the system agree to a set of rules. The first rule is that the workers Q1 and Q2 will call Q back at a predetermined time interval. The only reason when they won't call back is if one of them gets a call from P first. The other rule is that P will call the ith worker of Q, Qi, if it wants to indicate a 0 at the ith bit. So in this case, since P wants to indicate a 0 at the first bit, it calls the worker Q1. Now at the predetermined time interval, Q1 and Q2 must both call Q back, but Q2 is the only component that calls Q since Q1 has already been called by P. Now at this point, Q has gotten a call from Q2, which allows it to guess that Q2 signifies the bit 1. Since Q2 has called, it must not have been called by P. So Q correctly guesses the data bit 0, 1 since Q2 symbolizes the bit 1 and the absent call symbolizes the bit 0. Now floating labels are not only not secure, they are also not practical on Android. So say you have a component or a subject that provides a shared service to other different subjects in the system. And let's assume all of these other subjects have different labels. So initially, all of these subjects in the system call A, and A accumulates a label that is a join of all of their labels. Since we're using floating labels, this is the exact enforcement that we want. Now when A replies to the calls by all of these subjects, this huge label that A had accumulated now propagates back to all of these subjects. So what we really have here is a huge label that no single security principle can declassify, which is propagated to most parts of the system that are not isolated. And this problem is known as label explosion. And this problem is especially serious on Android because on Android, the component A could be anything. It could be a service or a content provider component. These are actual Android components that are shared amongst applications. It could be a file that is shared by multiple instances of the same application, irrespective of whatever secrecy context they're in. And it could also be a general purpose application like a PDF reader or an image editor that's called from many different secrecy contexts by other applications. So this problem of label explosion is really drastic on Android. Now we're going to talk about the challenge of network declassification on Android. So like I said before, data must be declassified before it is exported to the public domain, and the network is considered to be public. Now there are two primary ways in which declassification is being done right now. The first way is to query the data owner to declassify the data. So essentially you call back the data owner and the data owner either allows or denies the declassification. The other approach is for the data owner to actually specify a small set of security principles that can declassify data on its behalf. Now both of these approaches are problematic. The first approach is problematic on Android because Android is extremely network driven. Right? You have many applications that are continuously connecting to the network. And in such a network driven environment, it is very inefficient to continuously call back the data owner. The other problem is that when you specify other security principles to declassify your data for you, you then include them in your trusted computing base, and this is dangerous. Other than that, using only a small subset of applications to declassify data prohibits the user from using a third-party client to export data to the network. So the user is prohibited from using a third-party email client or a third-party cloud client to sync with the very servers that any other regular permitted client would do. So now that we've described all the challenges, I present Weir, a DIFC system that provides secure as well as backwards compatible enforcement for Android. Now our system Weir uses two techniques for such enforcement and for solving the challenges that we described before. The techniques of lazy polyinstantiation and domain declassification. Now polyinstantiation is best understood in our context when you compare it with explicit and floating labels. So to give you a brief recap, in explicit labels, when P calls Q, P and Q have to adjust their labels in order for the call to take place, otherwise the call is simply denied. In case of floating labels, the call is always allowed and the restrictions are simply propagated from the caller to the callee. And we've already seen the problems with this simple propagation. Now, when you combine floating labels with polyinstantiation, the following happens. The current instances of P and Q have different labels and P is going to call the component Q. But this call is not delivered to the existing instance of Q. Instead, a new instance of Q, Q prime, is created in the secrecy context of P, that is with the label of P. So what we are essentially doing here is we are making floating labels context sensitive. That is, we are creating instances of different parts of the system, say components or processes or files, for every different secrecy context whenever the call demands it. So why is this lazy? Well, first of all, like I said, polyinstantiation is event driven, right? We only do it in succession of a call. And the other thing that makes it lazy is that the operating system keeps track of all existing instances. And a new instance is created only when it is required, only when it doesn't exist in the required secrecy context. So if a new call came in for the component Q again, and in the secrecy context LP, that call will be delivered to the component instance Q prime that is already created in the context LP. So a new instance would not be created this time. Now, polyinstantiation is resistant to the data leak in floating labels that we showed before. So the figure on the left is the data leak in floating labels, and the figure on the right is how it's going to happen with polyinstantiation. So again, P wants to transfer the data bits 0, 1 to Q without actually transferring the label, and Q has created 2 workers for this job. Now note that Q's workers currently have an empty label, whereas P has the label L1. So when P calls Q1, instead of the call being delivered to Q1, a new instance of Q1, Q1 prime is created in P's secrecy context, and a call is delivered to it. So as a result, when the time interval comes for Q's workers to call Q back, only Q1 and Q2 call Q back. And Q will always get these data bits 1, 1, irrespective of what the actual data is, because we'll always keep creating context-specific instances of Q's workers. Now, it is also easy to see why polyinstantiation makes floating labels resistant to label explosion. Since no single component is ever going to accumulate labels, since we are always going to create instances for every different separate secrecy context, you're never going to see a label explosion. You're never going to see label accumulation in the first place. Also, if we polyinstantiate processes, which we do, then you will never have multiple secrecy contexts coexisting in the same process. For every separate secrecy context, you will always have a separate process. So you get process level labeling without the resultant false positives. Now we designed polyinstantiation on Android in terms of memory and storage. For memory, we created separate instances of processes as well as Android components in terms of the caller's label. And on Android, developers can specify a mapping between processes and components. So developers can specify a component to run in a specific process. And we can maintain this mapping in our approach, but per secrecy context. So we cannot really maintain cross-context secrecy mappings, and it doesn't even make sense, because in every secrecy context, every process and every component is available. So that mapping can always be made in that particular secrecy context. Now in terms of storage, we created context-specific layers for each secrecy context to access the storage. So every label has its own layer through which to access the default unlabeled file system, and layers cannot, and processes in an unlabeled labeled secrecy context cannot directly access the file system. So for transparent storage access, processes in labeled secrecy context can read from any file, unmodified file on the default file system. But once they try to modify a file on the file system, the file is copied over to their layer, and then the future modifications and future reads and writes are made to that copy of the file. So why does this work on Android? Well, on Android, the developer is forced to adopt a very stringent application model, where the application is composed of specific types of components, and where each of these components has its own specific API, and more importantly, can be called in only a certain specific number of ways. So all the communication between components is initiated through a system service, the activity manager service. So this communication essentially is indirect. When one component calls another, the activity manager chooses the instance of the receiver that should actually receive the call. So the caller can specify who to call, but not the instance that should receive the call. So there is this fine distinction between specifying the component's identity versus specifying one of its many instances that must receive the call. And we extend this exact indirect call mechanism for a context-specific polyinstantiation. Now there is also direct communication in Android through the binder RPC, but again, for such communication to take place, you first need to establish a connection between two components, and for that you again need to go through the indirect route. So we can still leverage polyinstantiation that way. Finally, I'll present the primitive domain declassification that we use for network declassification on Android. And the intuition behind this is very simple. So in Android's network-driven environment, it makes more sense to reason about where the data is going to be delivered rather than what client is performing the export. So what we really do is we allow data owners to reason about trust in terms of web domains on the network rather than applications on the device. And whenever data is to be exported to one of the domains trusted by the data owner's security tag is simply declassified. We implemented a system on Android 5.0.1, and our implementation is open source. I encourage you to check it out. We use the Flume policy model, a specific policy model for our implementation, but then our mechanisms, as we've described in the paper, are policy agnostic and can be adapted to suit other policy languages. We ran some microbenchmarks for our performance evaluation and microbenchmarks for common operations such as starting components or reading and writing files, etc. And we did not notice any high overhead in terms of the absolute value when we compared the performance of our system with that of vanilla Android. We also evaluated the scalability of starting a single component when a large number of its instances already existed in the system. So we started up to 100 instances of a component and then started the component just to measure how long it takes to start it. And we noticed a very linear rise in the start time of that component. Even for the final instance where we started up to 100 components, the start time was only delayed by 50 milliseconds. Now in the paper we described why the start time of a single component is affected by its concurrent instances, but the concurrent instances do not affect the global start time. I would encourage you to go and read it. Now we executed a case study with a K9 email application, an application that is a very popular email client. And the objective of this case study was to separate personal and work email data within the same application simultaneously. So what we did was we configured K9 email to use both the user account as well as the enterprise account, like many of us do. And then we simulated business data through an application known as bcloud. So we created the bcloud application to import some business contacts and business documents onto the device. Now what bcloud does is that before sharing this data with any other application on the device, it creates a policy, an enterprise policy for its data. And the enterprise policy is a very simple domain declassification policy. It says that bcloud's data should only be exported to the domains belonging to bcloud.com. That's it. That's the policy. Now to run the case study, we shared some data from the bcloud application with the K9 email application, and the data opened in K9 email's compose window. Now in the compose UI, we added contacts, we tried attaching documents, but we did not send the email. Instead, we switched back to the home screen. Now we opened up another application and shared some unlabeled data with K9 email and repeated the procedure of attaching contacts and attaching documents. Then we quickly toggled between the two instances of K9 email in both the contexts and sent out both the emails. Now a general observation was that instances of K9 email existed simultaneously in both the contexts, in the secret context of bcloud as well as in the non-secret context. Now specifically in the enterprise context of bcloud, we observed that we could see data from the labeled layer, that is bcloud layer, as well as we could see the unlabeled data from the unlabeled file system, whereas in the unlabeled instance of K9 email, we could only see data from the unlabeled file system. Also in terms of network export, we observed that in the business context, K9 email was constantly being denied connections to the personal accounts. And this is essentially domain declassification in action. Now we also observed a couple of caveats of our approach when we ran this case study. Now like I said before, we observed that we could see labeled as well as unlabeled data in the labeled secrecy context. But at the same time, what if the user wants to see different kinds of labeled data in the same context? What if the user wants to see medical and financial and enterprise in the same context? In that case, you would need an application that actually accumulates labels rather than suffers from polyinstantiation. So essentially, you would need an application that is a system app that can be trusted and can override polyinstantiation for its workflows. The other caveat that we observed was that updates made to files on the default layer were not actually being propagated to their copies on labeled layers. So essentially, what we observed was that the contacts from the unlabeled context that we saw in the enterprise instance of K9 email were actually their old versions. The updates that had been made to the contacts on the unlabeled layer had not actually been propagated, and this is actually a very hard problem that results from using a file layer copy and write mechanism. So to summarize, we need DIFC on Android if we want to keep using application data sharing without the risk of unauthorized data disclosure. At the same time, enforcing DIFC is really hard when we can't solve the problems associated with floating labels. So our approach makes floating label enforcement context sensitive, thereby making it possible to use on Android. That said, there are still some open challenges. Now we've already discussed the first two challenges of a centralized perspective or of propagating changes made to the default layer. The other challenge is that of instance explosion. So an application could launch a denial of service attack on another application by starting a large number of instances of that application, and that is possible, and we are trying ways to rate limit instance creation in order to prevent that. The final challenge that we're trying to deal with is that of defining trusted domains. So defining trusted domains for domain declassification. And that essentially is a policy specification challenge. So with this, I end my talk, and I'll be happy to take questions. Thank you.
Questions?
Orlins Fernandez, University of Michigan. So when you explain floating labels with polyinstantiation, I don't understand why, I think on slide 15 and 16, why W prime cannot just contact the recipient of the bits.
Could you repeat the question, please?
Like on slide 15 or 16, when you introduce floating labels with polyinstantiation, yeah, why can't that Q prime, yeah, just contact Q?
So Q prime is a fresh instance of Q1 that is created from a static copy of Q1. So Android components always have a static definition, and new components are created from the static copy. And Q prime is just a copy of the component Q1. Now, Q prime is just like Q1 and Q2. Q prime is programmed to contact Q only if it has not been contacted by P first. So since Q prime has been called by P, it will not call Q back. That is the whole point of this attack. Now, if Q prime really calls Q, then Q gets the label L1 and the attack is defeated.
I see, but P has called Q prime here, right?
Right. P has called. So the way this works is that P calls Q1, but the call is intercepted and diverted to Q prime, and the operating system does that.
I see. Okay. Okay. So actually, it was a call at Q1. But
right, and P is completely unaware of this. P is even unaware of that it has actually been delivered to Q prime.
Yeah. Thank you.
Sure. Wow.
Hi, Sven Mugir, Saarland University. Very nice work, first of all. Two short questions. The first about the network declassification and creating of labels. So applications today make more and more use of web views to integrate like platform independent languages. And web views can interact with the system through Java bridge code. So in declassification and creating labels, when you have web views with potentially different origins, do you consider this? Or, I mean, this could be a cool extension for
right. Yeah, I see your point. So whenever we start a new instance of an application or a component, we start it based on the caller's context. Now, if there are calls from different contexts, the web view will be reinitialized. So we do, to some extent, we do polyinstantiate web views, but they're just created as a part of their parent activity instances.
Okay, but it also has to the way work back. So if data is coming in from the network, you also probably have to.
So if data is coming into the network, it will still keep coming into the instance that is already active. That instance won't be disturbed. You'll just create another copy that will execute that particular call. And the way activities work is that they react to the call, right? So if there's an activity that has a web view, it is also going to react to a call that it gets based on what the call's attributes say.
Okay.
So it is going to initialize the web views according to call anyways.
And secondly, a very short question. You create the instances also based on the labels assigned to files. I presume these labels are persistent. So if the file is, if the application that created this label is deinstalled, you might have like dangling labels that might be a problem then that have to be cleaned up or.
Right. So polyinstantiation partially solves this problem. So an application can only leave dangling labels to its own internal files, which are deleted anyways on Android. So on Android, if it's your internal directory or if it's your external directory, it's deleted when the application is uninstalled. So the files don't remain. Now, when it comes to common files that the application can write to, those files are still context specific. So we are still looking for ways to use other applications, super user applications for the user that can actually allow the user to pick a different label and view files of that label. So the files would still be accessible, and you're right, the label is persistent, so otherwise there would be dangling labels. But that's still a part of the usability aspect of the approach that we're looking into.
Okay, thank you.
Hi, great work. Amir Ramadi from University of Michigan. The polyinstantiation doesn't really take care of the dead man switch side channel, does it? So if, for example, Q1 knows that it should be contacted by P in a given time. And if such a contact isn't made, it knows that it probably gained that label. Then it could still transfer to Q that this hasn't happened.
Yeah, I see the point you're trying to make. So if Q1 knows that it's supposed to be contacted by P in a certain time, and if P already has a label, say P already has a label L1, even if P calls Q1, the call will not be delivered to Q1, but it will be delivered to another instance of Q1. So that instance of Q1 will be labeled accordingly, so it will not escape the label. And this existing instance of Q1 will still keep thinking that will still be ambiguous. It won't know if the data, if P even exists, or if P has made the call, or if P already has the secret data.
True, but doesn't that instantiation create an obvious time difference, timing side channel? So the time it takes to instantiate compared to the time when Q1, the original Q1 would contact you, there would be a difference in timing, right?
So it may create for a conventional system, but for Android, where most of the communication is indirect, application components cannot really observe the time for instantiation before they're actually instantiated. So before you instantiate it, you don't know actually when the instantiation started. There is no way for a component to know when the call was actually made unless it has some communication with the caller.
Okay, thank you.
All right, thank you very much.